propagation is the master algorithm that lays the foundation of the deep neural network training process. It uses the concept of derivative to optimize the weights of the deep neural nets. Today I want to show you the mathematical definition of the derivative, and then we'll switch to the Python code to build a better intuition behind this concept. Let me show you a quite simple example. Let's define function f of x equals x squared. And we know that the f prime of x in this case equals 2x. To build a basic intuition behind this, let's write down the mathematical definition of the derivative. We know that the f prime of x can be defined as the limit h goes to 0, and in the body of this expression we have a fraction. So fraction, it's some sort of ratio. Let's try to understand what kind of ratio do we have here. As the first term in the numerator, we have we have a function with x plus h as the input. What is the meaning of this operation, x plus h? We can ignore this limit expression and use this h as a tiny value that we add to our original input. And then we subtract from this first expression our second term, f of x. So the basic meaning of this operation, it's kind of value that shows us how our function gonna react for this tiny change in the input. So if we have negative value, it means that our function decreasing. If we have positive value, our function just increasing, because we change our input just for a little and then subtract our function with the original input, yeah? And in case if we have 0, means that we have no change, we have no reaction from this input change. And to create a ratio, we just divide this result by h. And we have a value that shows us how our function gonna react for this change, and then we divide this by the value of our change. Meaning this whole limit expression basically just the rate of change of our function. Let me show you that this expression works fine for our example, for our function f of x equals x squared. Limit h goes to 0. Looks like we have this first term fx plus h, and we have our function f of x equals x squared. We take our input and put it right over here. That basically means that we need to square our input, x plus h squared. And then we subtract our function with the original input, x squared, and divide it by h. So let me simplify this expression, and we have x squared plus 2xh plus h squared minus x squared over h. Now we can simplify it a bit in this one, and as the result we have limit h goes to 0, and we have 2x plus h. And it's very easy to solve, yeah? Our h goes to 0, we can replace this h by 0, and we have the just 2x, yeah? Just 2x as we expected. Oh, mathematics works fine, yeah? To build a better intuition behind these mathematical expressions, let's program these functions and then visually represent what's really going on behind this. Let's define a function f of x, and f of x equals x squared. So we need to return x squared. It's basically absolutely the same expression. So then let's define df of x, as derivative of f of x. And we return 2 times x. So, and last but not least, it's right over here, this expression. But we have limit right over here. How can we program, the limit expression? Let's drop this limit expression and just use this h as a tiny value and put it directly to the ratio. This is very easy to implement. Let's define function numerical difference, and we have f as the argument, x, and h. We can define h as a tiny value, let's say 10 to the negative 2 power. And then we need to return f of x plus h minus f of x and divide everything by h. And basically it's exactly what we need, it's just a ratio, but in Python code. Right now we need to check how it works. Let's run this cell. We initialize these functions. Now we can check how it works. Let's define an input x equals 3, and then we can call f of x and save it to the variable fx. Then the same for the df. dfx, so we call df of x. And ndf of x, we can call numerical difference, and then we put function f, input x, and I don't want to touch h at the beginning. So let's check the output. F of x, dfx, and ndfx. And you can see that x squared equals 9 works fine. 2 times x, 2 times 3 equals 6 works fine. And the last result, it's very interesting, We have a pretty close value to the real derivative, So it's 6.009. And if we change our h, let's say we just decrease this value h to the negative 3 power, you can see that the error just decreasing. Let's take -4, and you can see that this error smaller and smaller every step. And now let's check how our function gonna react for different values of h. So we need to create a list of possible h values. Let's use a range between 1 and 15. And then we raise 10 to the negative p power. Let's print just to be sure that everything works fine. And you can see that we have 15 values of h, and it's between 0.1 or 10 to the negative first power to 10 to the negative 14 power. Okay, let's iterate through our values of h. And then we need to compute ndif. Let's call it ndfx. We call ndif for function f, and we need to take an input. Let's set up the input as x equals 3, exactly as for the previous example. Okay, and now we need to, instead of this fixed h value, we need to use our variable h. So then let's create a list of absolute errors. Absolute errors. and we need to add to the absolute errors list an absolute value, and we take our numerical estimation of the derivative and subtract from this our exact value of the derivative, and we know that this is just the df of x. Okay, and you can see that there are a bunch of errors, and it's quite interesting that the last one is higher than the first one. Yeah? Now let's import matplotlib.pyplot as plt, and then let's make a plot. Okay, and you can see that we build a figure. We use the log scale and h values against the absolute errors. For the x label, we have step size or h value. For the y label, we have an absolute error value. And let's just run this code and we can see this plot. Yeah, it's very interesting. We can read this plot from right to left because we reduce every time we reduce the step size. You can see that for the step size 10 to the negative first power, we have absolutely the same absolute error. And then every step we are decreasing the step size and everything works fine. Our error decreasing with the step, but till the 10 to the negative 8 power. Then we have this inflection point and our trend just completely changed in this point. Then it's increasing every step. And for the 10 to the negative 14 power, we have the error that is higher than for the 10 to the negative first power. And looks like our basic approach, it's not the best way to estimate the numerical derivative. There are three possible ways to estimate the derivative numerically. At least I know about three possible ways. Now let me write it down. We used the forward mode. Let me write it again. df with respect to x approximately equals to f of x plus h minus f of x over the h. It goes forward because right over here we change our input in the positive direction. We just add to our original input a tiny value. Then we subtract our function with the original input and divide by h. And we have the rate of change in positive direction. Yeah, how our function gonna react if we change our input in the positive direction. And it calls the forward mode. We have one more way. It calls the backward mode. df with respect to x can be approximated as the f of x minus f of x minus h over the h. It goes backward because we change our input in the negative direction right over here. We just trying to measure how our function gonna react if we change our input in the negative direction. What will be the rate of change after the changes in the input for this tiny value h? And it calls the backward mode. And the last method, it's the average between these two. So let me write it down. df with respect to x approximately equals f of x plus h minus f of x over the h plus f of x minus f of x minus h over the h, and everything we just divide by 2 because we wanted to find an average. Okay, let me simplify this expression, yeah? So I can immediately replace this by the common fraction. So we can just drop negative f of x and f of x. And at the end of our simplification, we have only f of x plus h minus f of x minus h over 2h. And this last method, it calls the central mode, the central difference. Central difference. And for the most cases, this central difference is the most accurate, the most precise method that we can use to get a numerical estimation of the derivative. Now I want to program these 3 different approaches and then just compare how it performs, yeah? What will be the best method for the numerical estimation of the derivative? For the forward difference, we already have an implementation. We have this ndiff function. We can just copy and paste it right over here, yeah? And let's call it fdiff instead of the ndiff. So then we need to program the backward difference, yeah? So let's define function backward diff. We have the same bunch of parameters, f, x, and h equals 1e to the negative 2 power. And we need to return, so basically we have a fraction, and as the first term we have f of x. As the second, we have minus f of x minus h. Yeah? Let me check it again. F of x minus f of x minus h. Yeah, looks good. And let's program the central difference. So we have c diff, yeah, as the central difference. There's the same bunch of parameters right over here, and we need to return a fraction. In the denominator, we have 2 times h, and in the numerator, we have f of x plus h minus f of x minus h. Yeah? Now I want to implement a function that visually represents errors from these 3 different approaches. Let's call this function plot errors. And we have function, derivative of this function, and input. And first of all, we can compute dfx. For this purpose, we need to call df with the argument x. Okay, also we need this bunch of possible h values. Let's add it. Okay, so then we have forward errors, backward errors, and the central errors. We can define it as 3 different lists, and then let's iterate for this list of possible h values, and we need to add to the forward errors absolute value. For the forward difference, and we use f, x, and h value right over here, and then we subtract the real derivative. Okay, great. The same we need to do for the backward errors, but we need to call backward difference, and then for the central difference. And we need to call the central difference. Okay, and now we add a figure and we represent this forward, backward, and central difference against possible h values. And now let's check how it works for our example. I just want to copy this code and paste it right over here. Just, to keep everything in one place. Yeah, I want to have everything in one screen. So we have this f function and df of x. Then let's plot our errors. For this f function, we need to put as the second argument the derivative of this function, and we know that we have this x squared and 2 times x for the derivative of this function. And last argument, we need to provide an input. Let's initialize x equals 3 and then put this input right over there. Okay, let's run this code. Okay, and you can see how it looks. Let's read this plot from right to left. And from the beginning, when the step size is 10 to the negative first power, you can see quite opposite results. For the forward and backward difference, it's kind of match right over here at the beginning. And for the central difference, it's absolute opposite result. We have approximately the same absolute error rate for the backward difference and forward difference, 10 to the negative first power, but for the central difference, we have 10 to the negative 14. It's almost perfect match at the beginning with this step size, 10 to the negative first power. And then every step, our error are increasing for the central difference, and it's different behavior for the forward and backward difference. We can see this step by step decreasing of the error. Yeah, then we have this intersection between the central and backward difference, and both of them just increasing, yeah, every step after the step size 10 to the negative 8. So we can see that for our example, it works almost perfect when we use the central difference, yeah? But let's implement bunch of functions and then visualize errors for every function. Okay, and let's import NumPy and define, let's say, function exp. And we need to receive just x as an input value and return numpy.exp for our value x. And we know that the derivative of the exponent is the same exponent. Yeah, it's quite easy. Derivative of the exponent function, just return the same numpy exponent. And we can copy this input, this code, and we need to take an exponent, then the derivative of the exponent, and let's run this cell. For the exponent, we have not so big difference, yeah, between the central difference and forward or backward difference. But for the 10 to the negative 5 power, we have very big difference. Yeah, it's quite obvious that right over here in this point, yeah, central difference works very good compared to the backward or forward differences. Let's implement more. Let's define function sine of x, and we return numpy sine of x. And we need to implement derivative of the sine of x. And we know that the derivative of sine of x just the cosine of x. we need to return numpy cosine of x. Okay, great. And then let's visually represent the result. We need to change exponent to the sign and the exponent to the d sign. And here I have input 3. Okay, and here we go. Again, at the point 10 to negative 5 power, the central difference just totally dominates this forward and backward difference mode, yeah? At the beginning, it's quite small difference, but then it very rapidly goes to 10 to the negative maybe 11 or 12, I don't know, it's something like this, yeah? So it's similar behavior, yeah, for the exponent and for the sign. Let's try one more. And we define the tanh of x. We return numpy tanh of x. And let's define the tanh of x. And in this case, we need to return 1 minus numpy tanh of x squared. Yeah? And let's use our plot errors function. And you can see that tanh and dtanh run this code, and you can see it's again, yeah, very similar result, yeah, very similar with the exponent, with the sign, yeah. Okay, and for most of the cases, central difference just more precise than forward or backward difference, and probably it's one of the most precise methods to estimate the numerical value of the derivative.